far beyond the comfort of Earth's warm atmosphere, where blue skies fade into endless darkness, lies a reality that seems almost impossible to understand. A reality where one side of an object can be scorching hot, while the other side freezes in silence. A place where astronauts floating only a short distance from intense sunlight can experience temperatures colder than the most extreme environments on Earth. This is the strange and fascinating nature of space. Because despite being surrounded by stars that burn with unimaginable power, the universe itself is overwhelmingly cold. At first, this makes no sense. After all, our entire existence depends on the energy of a single star, the Sun. This enormous sphere of nuclear fusion releases more energy in 1 second than humanity has used in its entire history. Its surface blazes at thousands of degrees. Its core reaches temperatures of millions of degrees. Radiation streams outward in all directions at the speed of light. On Earth, even standing in sunlight for a few minutes can make your skin feel warm. So naturally, a simple question emerges. If the sun is so incredibly hot, why isn't space itself filled with heat? Why doesn't the region between planets boil with energy? Why do spacecraft need heaters to survive, even while orbiting close to this giant cosmic furnace? To answer this mystery, we must begin by understanding something surprisingly subtle: the true meaning of temperature. Most people think of temperature as a direct measure of how hot or cold something feels. But in physics, temperature has a much deeper definition. It describes the motion of particles. When atoms and molecules move rapidly, they carry more kinetic energy. This energetic motion creates what we experience as warmth or heat. When particles move slowly, energy decreases and temperatures fall. On Earth, we are surrounded by trillions upon trillions of particles. Air molecules constantly collide with our skin. They transfer energy through contact. They trap warmth close to the surface of the planet. This is why stepping outside on a cold winter morning feels so different from standing in a warm room. In both cases, temperature is not just about radiation from distant sources. It is about how energy moves through matter. And this brings us to one of the most important facts about space. Space is almost completely empty. Between planets, between stars, even between galaxies. There are vast regions where only a few atoms exist in each cubic meter. Compared to Earth's atmosphere, this density is unimaginably small. If you could scoop up a box of interplanetary space and bring it to Earth, you might find fewer particles inside than in the best vacuum chambers scientists can create. This near-perfect emptiness changes everything about how heat behaves. On our planet, heat travels in 3 primary ways. The first is conduction. This happens when particles collide directly, transferring energy from one to another. Touch a hot metal surface, and energy flows into your skin almost instantly. The second is convection. This occurs when warm fluids or gases move, carrying heat with them. Warm air rises, cool air sinks, creating currents that distribute energy across entire regions. The third method is radiation. This is the transfer of energy through electromagnetic waves. Unlike conduction and convection, radiation does not require matter. It can travel through empty space. The sun warms Earth through radiation. But here's the key. Radiation alone does not automatically make space hot. Because once energy leaves the sun, it spreads outward in every direction. Imagine turning on a flashlight in a dark field. Close to the source, the beam appears bright and intense. But as it travels farther away, the same amount of light spreads across a larger area. Its intensity decreases. This principle is known as the inverse square law. Double the distance from the source, and the energy becomes 4 times weaker. Triple the distance, and it becomes 9 times weaker. By the time solar radiation reaches the orbit of Earth, it is already vastly diluted compared to its intensity near the Sun's surface. And beyond Earth, the energy continues to fade. At the orbit of Mars, sunlight is noticeably weaker. At Jupiter, it becomes dim. In the outer reaches of the solar system, sunlight is little more than a faint glow. Yet even this explanation does not fully solve the paradox. Because even near Earth's orbit, where solar radiation is still powerful, space remains cold. To understand why, we must consider another crucial factor. Heat does not accumulate easily in a vacuum. On Earth, when sunlight warms the ground, air molecules trap that warmth. Energy bounces between particles, slowing its escape into space. This process creates stable temperatures that allow oceans to remain liquid and life to thrive. In contrast, an object floating in space can only gain energy when it directly absorbs radiation, and it can lose energy just as easily by emitting its own infrared radiation into the darkness. There is nothing around it to hold that warmth in place. This creates extreme temperature swings. A spacecraft exposed to direct sunlight can heat to over 100 degrees Celsius. But move into shadow, and temperatures can plunge below -100 degrees within minutes. Astronaut suits are designed to handle these dramatic changes. Inside each suit is a complex thermal control system. Pumps circulate cooling fluids. Reflective layers deflect excess radiation. Electric heaters prevent freezing in darkness. Without these systems, human survival in space would be nearly impossible. The same challenge affects satellites and deep space probes. Engineers must carefully balance heat absorption and heat loss. Too much sunlight can damage electronics. Too little can cause systems to fail. Thermal regulation becomes one of the most important aspects of spacecraft design. These realities demonstrate an astonishing truth. The universe is not naturally warm. Warmth exists only where energy becomes concentrated. Stars act like temporary furnaces in an otherwise cold cosmic environment. Beyond their influence, temperatures fall toward one of the lowest limits physics allows. Scientists call this limit absolute zero. At absolute zero, particles possess almost no motion. Energy reaches its minimum possible state. While absolute zero cannot be fully achieved, the many regions of space come surprisingly close. The average temperature of the universe is only about 2.7 degrees above this limit. This faint warmth does not come from stars. It comes from an ancient glow left behind by the birth of the cosmos itself. More than 13 billion years ago, the universe was an incredibly hot and dense place. As it expanded, energy spread across greater distances. Temperatures dropped, matter cooled, galaxies formed. Today, astronomers can still detect this ancient radiation. It fills all of space like a faint whisper from the beginning of time. This phenomenon is known as the cosmic microwave background. It represents the thermal afterglow of creation, and it reminds us that the universe has been cooling ever since its origin. Yet, even in this cold environment, islands of warmth continue to appear. Stars ignite within collapsing clouds of gas. Planets form within swirling disks of dust. Atmospheres trap energy and create climates where life may emerge. Earth is one such world. Our atmosphere acts like a protective blanket. It absorbs solar radiation and redistributes heat across the planet. Without this greenhouse effect, Earth's average temperature would fall far below freezing. Oceans would solidify. Weather systems would vanish. Life, as we know it, would struggle to survive. Understanding the balance between radiation and insulation is therefore essential. It determines whether a planet becomes a frozen wasteland or a vibrant ecosystem. It shapes the boundaries of habitable zones around stars, and it will influence humanity's future as we venture deeper into space. Because one day, explorers may travel far beyond the warmth of the sun. They may journey into regions where starlight is scarce and temperatures approach the cosmic background. To survive, they will need advanced technologies, artificial habitats, nuclear power sources, self-sustaining ecosystems. The challenge will not only be distance, it will be cold. A cold so profound that it defines the very nature of the universe. Yet there is also something beautiful about this reality. Because in a cosmos dominated by darkness and freezing emptiness, every star becomes precious. Every warm world becomes extraordinary. Every living organism becomes a rare and remarkable expression of energy overcoming entropy. Perhaps this is why humans have always been fascinated by the night sky, like we are creatures of warmth, born in the glow of a star, living on a fragile oasis in an endless cosmic winter. And as science continues to explore this paradox of intense stellar heat within an overwhelmingly cold universe, we come closer to understanding not only space, but our own place within it. If this journey into one of the universe's greatest mysteries expanded your perspective, take a moment to like this video, share it with someone who loves cosmic science, and subscribe for more deep explorations into the hidden physics shaping reality. Because out there, beyond the warmth of our star, the cold silence of space is still waiting to be understood. As our journey through this mystery comes to an end, one truth becomes impossible to ignore. The universe is not a warm and welcoming place. It is vast, silent, and overwhelmingly cold. Between the scattered lights of distant stars lies an ocean of darkness where temperatures fall toward the lowest limits allowed by physics. Yet within this cosmic winter, islands of warmth continue to shine. Worlds like our own survive in a fragile balance of energy, absorbing radiation from a single star, holding onto that heat just long enough for oceans to flow, winds to move, and life to evolve. Every sunrise on Earth is a reminder of this delicate miracle. Because without the steady power of the sun, our planet would quickly become another frozen rock drifting through space. Understanding why space is cold while stars burn with unimaginable heat does more than solve a scientific puzzle. It reveals how finely tuned the conditions for life truly are. It shows us that warmth is not the default state of the universe. Warmth is rare. It must be created, captured, and protected. And as humanity looks toward the future, toward journeys to Mars, missions beyond the outer planets, and perhaps one day voyages between the stars, this knowledge will become essential. We will carry our warmth with us, inside spacecraft, inside artificial habitats, inside the fragile ecosystems we build to survive in environments that were never meant for us. But there is also something deeply inspiring about this reality. Because in a universe dominated by cold and emptiness, we are the beings who can create fire. We are the species that learn to harness energy, to understand physics, and to transform knowledge into survival. The same sunlight that warms our skin today once ignited the curiosity that led us to explore the cosmos. And somewhere out there, under alien skies, other civilizations may be asking the very same question. Why is their universe so cold when their stars shine so brightly? If this exploration changed the way you think about space, take a moment to like this video share it with someone who loves cosmic mysteries, and subscribe for more deep journeys into the science shaping our reality. Because the universe is still full of questions, and together, we are only just beginning to find the answers.